more local. That's not a problem for preparing the CAD state because, like we just saw, I mean, so this circuit is more geometrically local than this one.
Yeah.
Probably, if you arrange some out of line. But these check operators are harder to make local. Because they're sort of like, you want them to be non-local because you have to look for different places in the CAD state kind of. So this is making this local is a bigger problem. And then the third problem you have is like you need to know how do you evaluate your CAD state. I mean, so
you got it.
So there's got to be some sequence of measurements or some tomography or something you do to check that you did it. Yeah, so I guess what you do is you try the CAD state without any preparation. You try the CAD state with this check circuit, and somehow you do some tomography and check that this one is better than that one or something.
Gotcha. Do a bunch of times, see if there's higher fidelity or something.
Yeah, something like that. Okay. Let's see. These are just other examples. Oh, I don't know. You can think about this if you want. So here we're doing what's called post selection, where I condition on. So post select is just a fancy word for condition, or not fancy, but whatever. Where I condition on this measurement being 0, and the same thing there. It's kind of wasteful because if you measure 1, you have to throw it away and start over. And this is bad in practice. Like not only is that wasteful because you're throwing away 4 qubits, but also it means that it just makes your architecture a lot harder. Because you usually, I mean, you're preparing a CAD state, or you're preparing some state because you want to use it, like as soon as possible. And so if there's a possibility of that CAD state just failing, then you got to have another one ready. So you actually have to be preparing extra CAD states, but that's not good enough because it has to be ready and in the right place. So you need transportation to move CAD states from some other portion of the computer to the portion where you're using them. So it all adds up. So post selection, or like another problem in practice is these measurements are quite slow in a lot of technologies. So I prepared this CAD state. I checked this CAD state. Even if this measurement succeeds, I had to wait like half an hour before I finished it. Before I could use this CAD state for anything interesting. And if you're going to wait half an hour, I mean, there's all sorts of noises being introduced. So it makes your life a lot harder.
So there are better ways.
Yeah. So that's what I'm asking here. Do we have to post select? So maybe what you can do is you can do something like. So what I'm trying to do add. This is the same circuit as before. This is the same check as before. Except I'm not post selecting this. So now this measurement could be 0 or 1. And based on what you measure, you possibly apply a correction, an X correction to 1 or 2 or actually to 1 of the qubits. You can't apply correction to 2 qubits because then a weight 1 fault here would cause a weight 2 fault here. And so I'm trying to come up with a way of designing this. So designing which parity checks you make and what corrections you apply so that the output is fault tolerant. And yes. So
I guess
it's a question, right? It's not like I'm sure it's possible, but it's not obvious how to do it. It's not obvious that this is going to work or not going to work. And it's sort of like you kind of have to check it, I guess. Like you have to check all possible cases if there's a fault here, a fault there, a fault there, and make sure that for in every case you end up with at most a weight 1 error on the output at the end of the day. It certainly is possible. Like I'm pretty sure with 2 measurements you can do it. With only one measurement, I think you do have to do post selection. Okay. So did you have a question?
no, I think.
Okay. Cool. Give a fault tolerant circuit to prepare the 5 qubit CAD state using a most 1 and silica qubit.